So good afternoon. My name is Steve Haise. I'm the founder and president of Allsafe Industries. And first of all, we are so glad to have you guys as a customer. There's a lot of other departments in your community that are using RAE Systems equipment. So I always like to come in and give you guys some training so you're more comfortable with the equipment as you go along. So I've got a PowerPoint presentation we'll go through. The first segment is a lot of information I'm going to throw at you, but it's important just to get everybody on the same page. And then we're going to get some hands-on in the second segment, and then we'll talk about a few maintenance items in the last segment. So just kind of cover our outline here. Gas detection 101. That's always important just to make sure we're all using the same terminology and reading from the same sheet of music, if you will. Then we'll go over a RAE Systems product overview. How many are familiar with RAE Systems? Oh, is this new for you guys? Okay. We have a lot of departments that go from old RAE stuff to new RAE stuff, so this will be new information for you, so I'll make sure you're up to speed on how to use the equipment. We'll go over daily use and also monthly maintenance, because gas detection does need to be maintained properly if you want it to work right every time. And then we'll go over a few advanced maintenance functions, and that might not be everyone in the room, but whoever your gas meter guru is will really need to pay attention during that segment just to know how to change out sensors and things like that. And then we're going to go over wireless gas detection. I'm super happy for you guys. You're on the path to having wireless gas detection, so I'll talk through the segments on that to make sure you're comfortable on how that's going to work for you too. It's really ultimately going to make your job easier, so it's a good thing that you guys went wireless. Okay? And then I always say this, and guys, this is your training. I'm just here to facilitate, so please stop me and ask questions as often as you like. What I'll do is just stop when you have a question. And again, this is your training. So if you guys had something happen a month ago, 6 months ago, and you just want to kind of talk through it together, please do that. This is what this is all about, is to plug in a new piece of equipment to the way you normally operate so that you can be safer when you're doing it. Okay? All right. So the number one thing with gas detection, your primary goal is to get the air that you're about to breathe or work in to the sensors in the instrument. So there's a lot of little things going on in that statement, okay? So again, it's the air that you're about to breathe or work in, because we don't want a toxic gas that's going to be dangerous to your health. We certainly don't want a flammable gas that could make something explode when you're in the space, to the sensors in the instrument. And so that's important. So that kind of speaks to making sure you have the right accessories and making sure that the pump module and the unit's working properly. So just kind of come back to this statement, get the air you're about to breathe or work in to the sensors in the meter. If you kind of keep that as your baseline, you'll be good to go, okay? So the first thing I like to do is to cover the acronyms. There's several acronyms when you're talking about gas detection. The first being 4-gas. Pretty self-explanatory. 4-gas instruments typically monitor 4 gases simultaneously, and usually that's for confined space entry. And so OSHA is very specific on the gases that you test when you enter a space. It's oxygen first, then you check for flammable gases, and then you check for your toxic gases. So we'll talk about the difference between 4-gas meters and multi-gas instruments. And so that's one of the meters that you guys purchased, is a multi-gas instrument. And what makes yours different, it's a 4-gas, but it's also an extra sensor that we'll talk about here in a second. So I mentioned flammable gases. We measure that with an LEL sensor. The acronym stands for Lower Explosive Limit. How many have heard that term before? Okay, a few hands going up. So again, I've got several slides to explain LEL. I want to make super sure that you guys are comfortable with that term. And then I know the next acronym, TIC, could stand for Thermal Imaging Camera, but in this class, what is a TIC? Those are your toxic industrial chemicals. So you guys probably already know what companies in your area have toxic industrial chemicals. You're already making sure that you're prepared for that, because if there's an emergency, you know they're going to call you. And then, of course, you've got all the roadways in your community, so there could be any sort of tanker truck or freight truck coming through that could be carrying toxic industrial chemicals. So we'll talk about how you'll use your gas detection to measure that. And then this is the new sensor that we're adding to your multi-gas instrument, a PID. Anybody know what a PID stands for? Okay, so it's photo ionization detector, and I have multiple slides on that one as well. And your PID sensor detects volatile organic compounds, so that's VOCs. See how there's a lot of acronyms? So that's why we need to get these out there. And then when we're measuring volatile organic compounds, one of the things we need to know about each specific compound is what is the IP, or the ionization potential. It's a very specific number, and as long as your PID is larger than the number of the compound, we'll be able to detect that with the PID sensor that's in your meter. Okay, so we'll talk quite a bit about ionization potential. And correction factors is what CFs are. You know, we calibrate the LEL sensor to methane, but it might not always be a methane response that you're on. You might be responding to something that involves hydrogen or acetylene. So the LEL sensor responds to a wide variety of flammable vapors, and correction factors will actually help you dial in to get a more precise reading. And so we're actually going to go through, I'm going to show you guys how to set correction factors so everybody's comfortable with that as well. And then who's heard of the term bump check? Is that a familiar term? See a few heads going up and down. A bump check is simply putting gas on the instrument and watching the sensors respond. There's really no better way for you to know that the equipment is working properly than to hit it with some gas, watch the sensors react, then you take the gas off and the sensors go back down to zero. Now you know that that meter is going to work right when you're using it on the job or in a confined space or wherever you might be using the gas detection. Okay? And that's different than a calibration. A calibration is where we're actually going into the menus, we're telling the instrument, hey, I'm about to calibrate you. You'll use the same cylinder of calibration gas, but this time the instrument will let you adjust the readings so that they're more accurate. So I kind of refer to a calibration as an accuracy adjustment, okay? Because that's all we're doing. We're getting into the menus, we're feeding it a known value of gas from the cylinder, and we're saying, okay, reset yourself to these numbers. We're adjusting the accuracy. So just like the scale in your bathroom, if you want to step on it and get an accurate reading, it needs to start at zero. Okay, the same thing with the cow gas. We know what value it is, and we tell the sensors to adjust to that. Okay? And then the last term is cross-sensitivity. I like to mention that because some sensors will respond to other gases instead of just the target gas that they are designed to detect. So a good example of that is your carbon monoxide sensor will have a cross-sensitivity reaction to the calibration gas we use on the PID, which is isobutylene. So nothing to be alarmed about. It's just you want to calibrate your CO sensor first so that then when you're calibrating the PID with the isobutylene gas, any cross-sensitivity won't matter because you've already calibrated the CO sensor. But it's important to know when cross-sensitivities may exist. I had a customer that had ammonia sensors, and they were getting some readings in a part of the plant. They knew there was no ammonia in this particular area, and so they called me and they started investigating. Well, it turns out the ammonia sensor is cross-sensitive to acetylene, and sure enough, they had a torch set up in the space, and they had a leak on the acetylene line. And so that acetylene leak had a reaction to the ammonia sensor, and so the gas meter did its job. It alerted them that there was some sort of gas present and some sort of reaction was happening so that there was a reading on the sensor. Okay? So a lot of terminology. You'll get more comfortable with it as we track through this. So the next thing I like to do is just go over the different types of gas detection instruments available, and I'm going to grab a few and I'll start passing them around the room. So the first type of instruments I'll just inform you about are the single gas instruments, okay? So I'm holding the ToxiRAE 3. This is a real simple single gas instrument, very inexpensive, really a throwaway instrument. It's only available for CO and H2S, but that's what a little single gas meter looks like. No pump, no nothing to it. You clip it on, you forget it's there, and it just monitors the exact gas that it talks about. This one's a CO, so I'll pass that around the room. And then I'm going to walk over to this table because this is your equipment, and you guys purchased single gas instruments as well. This is the ToxiRAE Pro. And you guys had a HCN sensor installed. So I'm going to pass this one around the room too. We want to make sure this makes it back up to the front table. But the neat thing about the ToxiRAE Pro is it has a window on the front of it so that any sensor you plug into this unit, that's what this is. So the way we purchase them, they're HCN, but you could easily remove this sensor and plug in another sensor, and this single gas meter would then measure that particular gas. Okay? So single gas meter, typically diffusion, so it's only responding to the gas right around the sensor, and you'll just clip this on your uniform someplace, radio strap, belt, however you like to wear your equipment, and then forget it's there unless it starts beeping at you, okay? So we'll pass that around. The next type of instrument is what I call a basic 4-gas meter, like we talked about at the beginning. So this is what RAE Systems 4-gas meter looks like. It's a QRAE 3. This one does have a pump to it, so we could use sample tubing to draw samples up to the instrument. You can usually tell a meter that has a pump on it because it has this filter riding on the top, okay? And so basic 4-gas in a confined space setup would be your oxygen, your LEL, CO, and H2S, okay? We'll talk more about the QRAE 3, but that's what a 4-gas meter looks like, so we'll get that going around the room. And then the multi-gas instrument. So I'll just grab one of the demos I brought for the class today. A multi-gas instrument could be a 4-gas meter. So if I only installed an O2, an LEL, a CO, and H2S in this meter, it'd be a 4-gas and a multi-gas platform. But what makes the multi-gas platform different is you can get into some of those other exotic type sensors, chlorine, ammonia, hydrogen cyanide, sulfur dioxide, the PID that I mentioned when we were going through the acronyms. So a lot of different types of sensors could go in this instrument, a little more sophisticated than your basic 4-gas meter, okay? And this is the other meter that you guys purchased, and I believe you have it in your budget to purchase some more of these. So this is the one we'll really spend a lot of time on when it comes to the hands-on portion of the class. Thank you. And then I'll just mention the difference between diffusion and pumped instruments. So diffusion instruments, like those single gas meters I passed around, those only respond to the gas right around the sensor. So that's more of a personal instrument. The pumped instruments, of course, could draw a sample to you. So let's say that you've got a field of drums and you know that something's leaking in there and it's too dangerous to approach it. You could lay down some tubing and bring that sample to you. Same as with confined spaces. If you've got a vertical space that you're going to enter, you can start to lower tubing into the space before you break the plane of the space. And I'm using those words because that's what the OSHA standard says. You will do your atmospheric testing before you ever break the plane of the confined space. So you just lower tubing in. The other thing about taking vertical samples is that some gases are lighter than air. Some gases are heavier than air. So if you have to climb the ladder from the top of the space to the bottom of the space, you want to make sure to take measurements from the top of the space all the way to the bottom of the space. Okay? We'll talk more about that as well. And then rechargeable versus alkaline. Everything you guys purchased have the rechargeable batteries on them. It's the latest in battery technology, so you can't overcharge the battery or damage the battery from having it on charge all the time. So one of the things I'll encourage you guys to do, and I know we're already thinking of that in advance, is find a home for the meter and then just let it be on charge all the time. That way when you go to pick up the instrument, it's ready to go all the time. If you do get to your MultiRAE, for instance, and you find out that the battery's dead because maybe the previous shift didn't put it back on charge, you do have an alkaline pack that you could install and you could run it off AA batteries. Okay? And then the last thing I want to mention is data logging versus wireless. Like I said at the beginning, you guys did purchase the wireless option. So wireless means we're actually sending that data out from the instrument, and we can capture that information with a reader so that we can get those readings on more than just the instrument. That's different than data logging. Think of data logging as a recorder. So data logging is where the instrument will record your readings, and then you can download those at a later date. Versus wireless is real-time readings that we're sending to a transmitter that's close by, okay? So then with gas detection, there's also a lot of accessories. So the first accessories we'll talk about are probes and tubing. Again, if you need to go in and around flanges, or maybe you're responding to a residence and they have their CO meter in their home is going off, and you're trying to help them detect where that carbon monoxide comes from. Sometimes you can use that probe to go in and around the water heater, the furnace, different things, trying to identify where that's coming from if you guys get that far into it. Again, the tubing is just useful to draw samples to you, whether it's in a hazmat situation or a confined space situation. As I pointed out earlier, your pumped instruments will typically have a filter on the top, And so you want to always make sure that you're using this filter. I've rebuilt pumps thousands of times, and it's always better to use the filter. It keeps out the dust and the dirt, and it's even a hydrophobic filter, so we refer to it as a water trap filter. That way, if you were to lower tubing all the way to the bottom of a confined space and start to suck up any liquids, the hydrophobic filter will stop it to a point. But as soon as you start seeing liquids coming, go ahead and get that tubing out of the space and off the instrument. More importantly, there are circuit boards in here, and circuit boards don't like to get wet, so make sure you're not ingesting any liquids into the instrument. So you always want to make sure you are using a good filter on your pumped instruments. Your charger, obviously, you want to make sure you keep up with that so that you can keep your batteries charged up. You guys also purchased calibration cradles, and the calibration cradles from RAE Systems have the ability to charge the instrument. So you may find that what we decide is you'll just let the meter live on the cradle, and that's fine. That will keep the batteries charged up as well. Okay? And of course, very important that you have your calibration gas. The calibration gas is what you're going to use to do a bump check to make sure that the sensors are working. And again, oftentimes you're just going to do that in real runtime. So the meter's running, you'll attach it to the cylinder of gas, you'll watch the sensors react. As soon as you're satisfied they reacted sufficiently, so I like to say about within 20% of the numbers on the side of the cylinder, you're good to go. The biggest thing we're watching out for when you're doing that bump check is you're putting gas on a meter and a sensor sits at 0. It's very dangerous, because what's to say that you're not dropping your tubing into a confined space and getting some gas to the sensor? We want to know that sensor's not going to read gas before our life is in jeopardy. So you always want to do the bump check to make sure that the sensors are reading properly. And again, you guys purchased the ToxiRAE 2 calibration cradle, and it's super simple. All you have to do is hit the bump button, and it will run the bump check for you. Okay? And remember, you need a cylinder for each sensor that's in your instrument. So if it's just a single gas meter, you just need the single cylinder of gas. If it's your basic O2, LEL, CO, and H2S, we can mix all 4 of those gases together, so they're all in one cylinder. And then the isobutylene gas is the other gas that would be required for your PID sensor. So we're going to talk about that in more detail as well. And then, as important as the calibration gas is, the regulator that's on the cylinder, okay? And the little piece of tubing. You would be surprised how 50 cents worth of tubing can stop you from using your gas meters if you have no way to get the gas out of the cylinder and to the sensors in the instrument. So we'll just talk real briefly about a couple different types of regulators. This first one is what we call a preset flow rate regulator. It's the one that has the on-off knob on the side. So what we like to recommend is to keep the regulator open when you engage it into the cylinder. That way, if there's any gas trapped in here, it's not burping it into the cylinder. Once it's engaged and you hear the gas flowing, then you can shut it off. And then you just have it at the ready when you get your instrument into calibration mode, and when the meter says apply the gas, you turn on the regulator and it starts to flow gas to the instrument, and the calibration sequence will start. When you're done, obviously, turn this back off so we don't waste any gas. And when you're completely done calibrating your meters, you always want to remove a preset flow rate regulator. The reason is if you don't get that turned all the way off, you could slowly bleed that out, and if you're doing calibrations once a month, the next time you come back to your cylinder, you'll look at the gauge and it will be empty. And I've done that so many times, it's very frustrating. No way around it other than to purchase a new cylinder of gas. Okay, so that's a preset flow rate regulator. I'll pass that around the room. And then the one I was showing on this cylinder, this one is called a demand flow regulator. And again, this is what you guys purchased. You needed the demand flow regulators to work with your calibration stations. But what's great about a demand flow regulator is it flows the gas at the exact rate that the pump in your meter demands it. So when you hook this up to a pumped instrument, the regulator will flow out the calibration gas. And I call it the perfect calibration because it's flowing gas to the instrument the same way it would pull gas out of a confined space and run the test on the atmosphere. So again, I call it the perfect calibration because it feeds the pump the exact amount of gas being demanded by the pump, and that's why we call it a demand flow regulator. So, can I use this regulator with this meter? No. Why? There's no pump. Great. There's no pump on this one, so I wouldn't be able to extract the gas through the demand flow regulator. You would want to use a preset flow rate regulator if you were doing a manual calibration on your single gas. The demand flow is only for pumped instruments or through a calibration cradle. Okay, so I'll pass that around too. All right. There's one thing I skipped. I want to make sure to go back and cover it. We talked about how it's important to have tubing for your gas detection instruments, but there's different types of tubing. So the clear Tygon tubing is what it's called, and Tygon is like saying Kleenex. It's a brand name. DuPont owns the word Tygon. But it's the clear tubing that we use when we're using our gas detection to drop into a confined space. And so that's exactly the right way to say it. The clear tubing is fine for confined space type gases, your oxygen, your flammable gases, simple gases like COH2S, because you'll notice this tubing will actually absorb some of the gas. And so I pulled this out of service from a fire service, and you can see that it's turned practically coffee color because it just shows that this tubing will absorb some gas. If you're trying to measure VOCs, volatile organic compounds, in very low part per million, you're going to want to use Teflon tubing. Again, it's a brand name, but if you looked at this under a microscope, it's a very slick, non-porous surface. And so if we're trying to measure 5 ppm benzene, I need to run that sample through Teflon tubing because it's going to give me the better opportunity to get the whole sample to the sensor in your meter. Okay? So if you're on a VOC run, a hazmat run, you're going to want to use Teflon tubing. It's the opaque tubing. If you're just everyday, common confined space type entries, then the normal clear Tygon tubing is fine. Okay? So next, I wanted to talk about the sensors, because the sensors are what detect the gas inside the instrument, and there's about 28 different sensors that you can choose from with RAE Systems. And so I've got a little handful of sensors here that I'm going to pass around. Take special note when you get to this one. It's the only metal-bodied sensor in the pile that I'm passing around. It is the LEL Sensor, and it has a metal body for a reason. So we'll get back to that. I'll pass those around while I'm talking about sensors. The oxygen sensor measures oxygen in percentage. And who happens to know what the percentage of atmospheric oxygen is? Anybody know that number? 20.9, right. So outside perfect atmospheric air, 20.9% oxygen. The unique thing about your oxygen sensor, it's the only sensor that starts at a number, and when it goes down, will go into alarm to let you know that you have low oxygen, but it can also rise to let you know that you have an oxygen-enriched atmosphere. Why would that be important to know, oxygen enrichment? Because everything burns in an oxygen-enriched atmosphere. So even your turnout can burn in an oxygen-enriched atmosphere. That's why we use O2 and acetylene on a torch setup, because it's a very hot burn that can cut through metal. So if your oxygen values raise up above 23.5%, you're going to get a high oxygen alarm. And again, that can be as dangerous as low oxygen, okay? So again, the oxygen sensor reads in percent. It starts at a number, and it can go down and go into alarm, or it can go up and go into alarm. Your other sensors are your toxic gas sensors. So for instance, carbon monoxide, hydrogen sulfide, ammonia, chlorine. You guys have your ToxiRAE Pros with HCN sensors, hydrogen cyanide. We've found that hydrogen cyanide comes from these man-made materials when they're burning. So all the things in our homes these days, the carpets, the plastics, the fibers, the foams, when that gets superheated, it starts to release a toxic gas, hydrogen cyanide. Very dangerous to firefighter health over time. So I love the solution for structure crews when there's the possibility of the superheated gases being hydrogen cyanide. Just stay on air longer. I'm sure you guys have an air truck where you can use as many cylinders as you need. That is really going to prolong your health into your retirement years. So just stay on air longer. And now you have your single gas ToxiRAE Pros to measure HCN. That'll be another confirmation of when it's okay to go ahead and get off air. Okay? All of these sensors read in part per million. And like I said before, there's about 28 different sensors available from RAE Systems. So to demonstrate the difference between reading in percent versus reading in part per million, I have this little video that I wanted to show. So think about the one space that you're working in. If you could divide that into 100 squares, when one of those squares measures gas, that'd be 1%. If you could divide the space into 1,000,000 squares and you get one square being the target gas you're looking for, it's part per million, and then down to part per billion, and even down to part per trillion. So kind of think about what your measurement range is when you're looking at these different sensors, because a couple of them are going to read in percent, and several of them are going to read in part per million. And again, just think about how small that is and why we need a properly functioning gas meter to tell us what those numbers are. You know, it's easy to say, well, I can smell hydrogen sulfide, but eventually your nose will go numb to it, and that's why you need a good gas meter to tell you when you still have hydrogen sulfide. You will have think it went away. It didn't go away. Your nose just stopped reacting to it, okay? So now let's talk about the LEL sensor. And again, the LEL stands for lower explosive limit. It's your lowest concentration of an air-fuel mixture where you have all the right properties for fire or explosion, okay? It's your combustible gas, flammable gas sensor, and it reacts to a wide variety of vapors, okay? So it measures the fuel leg of the fire triangle. So you guys know more about fire triangle than I do, but I've got it listed here. Of course, one leg of the fire triangle is oxygen. We know we'll have that because we're on planet Earth. Our ignition source is our unknown. We don't know when that might occur that could set the whole thing off. So we need to measure the fuel leg of the fire triangle, and we do that with our LEL sensor. So if you see the graph at the bottom of the page, and you see the picture of the gas valve, imagine that I could seal off this room, turn on that valve, and start to fill this room with flammable gas. So we'll start off in this bottom left-hand corner on that diagonal line, and as we start to fill the room with flammable gas, we're eventually going to reach that proper air-fuel mixture where all I need is a spark or an ignition source to set it off. That's considered the lower explosive limit. That's the first point at which my air-fuel mixture would ignite. But you'll notice that that line will continue to go through that middle danger zone to this point here where it ends, that's called the upper explosive limit. Because at that point, the flammable vapor has pushed out enough of the oxygen that now it has defeated the fuel triangle. There's not enough oxygen to support combustion, and now I'm too rich to burn, okay? So if we were a chemical plant or a gas pipeline, we want to be able to measure from one side to the other. That's called gas by volume. But in first responder world, in safety world, we're just concerned about 0 to 100% of LEL because the spaces we're in should not have a flammable gas present, right? And does everyone see the two little tick marks at the beginning of that diagonal line? That's where your sensor goes into alarm. So your first alarm will go off at 10% of the LEL. You'll get the second stage alarm at 20% of LEL. And we want to give you those alarms way in advance so that you can take proper precautions to either ventilate the space or evacuate the space or however you need to deal with the flammable gas being in an area where it shouldn't be. Now we have the different flammable gases that you might run into, and each one has its own lower explosive limit and upper explosive limit. So the first example is hydrogen. And look at the wide band that exists for hydrogen. I don't think it's a surprise to anybody that hydrogen is a very flammable gas. It starts early and it stays for a long time. So 4% gas by volume is your lower explosive limit for hydrogen, and 75% is your upper explosive limit. We also have methane, which you'll probably run into most frequently. Methane, also known as natural gas, that's what most homes are using to power their furnace or their heaters. And so 5.3% of lower explosive limit to 15% as the upper explosive limit. You can see the upper and the lower on propane, methanol, and then see down there at the bottom gasoline. And of course we knew this also, gasoline is flammable. And so it becomes flammable very quickly. So let me show you another video. And this explains how your LEL sensor is actually working. So let's see if this one works for us. So the LEL sensor that I passed around earlier, it's the only sensor that has the full metal body to it. It's got a metal centered filter on the top of the sensor, and inside the sensor are two catalytic beads. One is the catalytic bead that attracts the flammable gas. The other one is a reference bead. And so as flammable gas starts to enter that sensor, the catalytic bead will actually burn the sample. So your LEL sensor is actually burning the sample, and it compares the heat of the catalytic bead to the reference bead, and that's how the computer in the meter turns it into a number that we can understand. Okay? So remember that your LEL sensor is actually burning the sample. So a little side note is that your LEL sensor, when it gets all the way to 100, it believes it's in a flammable atmosphere, and it will actually turn the sensor off, because we don't want the LEL sensor to be the source of ignition, of course, and we certainly wouldn't want it to burn out. You could burn up an LEL sensor all in one sitting if it just sits at 100, and so it will actually turn the sensor off. So the only way to reset that is to leave the space, turn the meter off, turn it back on, let it go through its new warm-up sequence. Okay? So any questions about the sensors that we just talked about, the oxygen sensor, the toxic sensors, or the LEL sensor?